Hi there, welcome back to Human Systems Engineering 542, Foundations of Human Systems Engineering. Today we will be talking about use error. These are errors that occur while people are using products and systems and things like that. And I think it's important for us to all recognize that as humans, it's pretty much impossible to even go a day, probably even an hour, without making an error. And in fact, 1/3 of device failures in medical devices that result in suboptimal treatment, injuries, or death tend to be failures of device use rather than failures of the device itself. That is, the piece of equipment actually didn't fault. It turns out the person using the equipment ended up creating a fault or making a fault, and that ended up causing some kind of untoward consequence. The weak link, then, is neither the person themselves or the device itself, but the interaction of the person with that device. And of course, by now, you're probably getting pretty familiar with that kind of situation as you study human systems engineering. So you'll notice we tend to choose the word use error rather than user error. The idea is the blame should not be attributed to the user, but rather to the user device system. That is, there's something in the interaction of those two things that has gone astray. So often if you fix how the device presents the information, maybe how it organizes the content or receives input, you end up eliminating that use error altogether. So strike the notion of user error from your mind completely. Instead, refer to it as use error or use-related error, because it's not the user that's at fault here. Instead, it's the user and their interaction with whatever it is that they're using that's the problem. In fact, it's a lot more effective to improve the device than to somehow try to improve the user. So there's lots of causes for use error. Errors are intentional, so it's kind of pointless to try to control what people didn't intend to do in the first place. And so just blaming them or punishing people for making an error or things like that are really not going to do the trick. And in fact, just the opposite. Blame tends to encourage people to hide errors to begin with, to kind of sweep them under the rug. So a culture of shame and blame ends up reducing the likelihood of people even reporting the problems that happen sometimes in medicine. And we can't learn from errors that we don't know about, that go unreported. So it tends to be kind of a bad situation when we blame people for doing something. Here are some other reasons for use error. One is we tend to emphasize technology over the user themselves during the design. So engineers, of course, are trained to be experts in technology and systems rather than experts in human behavior, which is one of the reasons you guys are taking this class. Engineers have a tendency to learn little about human perception, attention, memory, judgment, decision-making, or emotion, those things that really matter to human beings. They don't know how to consider the strengths and limitations of the human user in their design. That word is supposed to be design there. As you can see, I made an error. Technology itself is complicated and it requires a lot of specialized knowledge and skill. Unfortunately, engineers have to spend so much of their time just getting the product to work that there's very little remaining time to think about how the end users are going to use it. They've got their hands and their brains full trying to just make the darn thing work. There's also this tendency towards feature creep, or featureitis, I sometimes refer to it as, which is a tendency to continue to add functions to a product whether those functions are needed or not. These extra features tend to complicate the design. They tend to hide the design's main purpose and basically kind of hide what could be an otherwise elegant solution. Most products are and should be designed to do one or two things with some variations. Yet it's tempting for us, especially people in marketing that are paying attention to what the competition is doing, to include every possible technical function and hope that that adds value to the product. But the fact is quite the opposite. It usually doesn't add value to the product. Instead, it just kind of makes the product more confusing, more hard to use. After a certain point, adding feature actually diminishes the value, and we should be aiming for just the right amount of features and functions. Another problem that leads us to error is assuming users will become experts with your product. The fact is, people end up using, lots and lots of product throughout the day and throughout the weeks and the months and so forth. The likelihood of them becoming really expert at yours is probably pretty low. It's just one of numerous products that they'll be using all the time. And just because you spent a lot of time designing it doesn't mean that they'll spend a lot of time using it, and most people will never become experts at your system. So please don't assume they will or require them to. Also, don't rely on training. People hate doing training. Often we treat it as kind of a safety net for design, but the fact is people have more than enough on their plate than to go off and spend time trying to learn how to use your product. They lead busy lives. They got other stuff going on. And as we know from our lectures on memory and so forth, our memory tends to decay so quickly that even users who receive really great training are unlikely to remember the details of that training when the time comes anyway. So do not rely on training. It doesn't mean don't do training. Training, often is something you have to do. However, don't count on it really helping you. The user interface itself during the time of use should be able to make it so that training isn't necessary. We often underestimate environmental challenges. What do I mean by that is the challenges that are represented just in the environment in which people are using the product to begin with. So, they could be using it in a noisy environment, an environment on the move. They could be using it in a plane where they've, have to crunch up their arms and try to use it like little Tyrannosaurus Rexes. Basically, the environments in which people use things are often suboptimal. But those aren't necessarily the places in which you've designed them. And if you're not aware of what those environments are, that could come back to haunt you and make it so that your device in that particular environment is particularly difficult to use. We also have this tendency to be optimistic in our designs, and that's probably important for us as people who create things. We need to be optimistic, but we should also, as often as possible, design for the worst case scenario. So for example, engineers, when they're doing reliability testing and so forth, conduct drop tests. They'll take something and drop it off a bench, drop it off a ladder, etc., just to see how resilient that particular device is. And, if it doesn't survive the drop test, they'll go back and figure out other ways to beef it up so that it does survive the drop test. Well, our example of a drop test for us is a usability test. That is, we have real honest goodness users conduct real honest to goodness tasks, and we keep track of whether they had success or failure, what types of errors they made, what kinds of problems and confusions they had, and so forth. And we go back and we beef our user interface up to make that more resilient too. That is, we need to take into account and create that worst case scenario and test people under that worst case scenario. There's also the notion that sometimes we just forget to expect use errors. We kind of create what we call the happy path for the design. That is where people, go the optimal way of getting from point A to point B every time. On the other hand, if we think about it, of course, we recognize that people aren't going to go down that happy path every single time. And in fact, they'll deviate from it quite a bit. And we need to be able to figure out how to rescue people when they've gone astray. So we should expect them to happen and design for the situations where that does happen. We often tend to underestimate the diversity of our users. Hopefully your products that you design will have just a giant number of users using them. But if that's the case, then they're going to be wildly variable. You'll have all kinds of people using them and so forth, and different people have different knowledge, different skills, different talents, and the lack of all of those things too. So as a result, we need to be paying attention to a wide variety of our users using this particular product, and we should probably usability test it with a wide variety of users just so that we can figure out what kinds of problems different kinds of people are going to have with our product and go through and address those problems, fix them basically before we let that product out into the world. Another one is often we expect people will be, especially for big systems, that people will be able to multitask. And as we've talked about in our session on attention, people are just horrible multitaskers. It wears us out, it takes all our energy, it fatigues us, it reduces our effectiveness by causing what we call interference. People simply do not multitask well. Please don't try to expect them to. And there's other causes of errors, use error as well. Sometimes we overestimate user capabilities and user motivation. Just because you're motivated to design your product doesn't necessarily mean somebody is motivated to learn it and then use it. Sometimes we fail to involve users early on in the design process, which is a big miss, because that's when we can really make the best, the best use of their input. And then finally, kind of relying on thought leaders. That is, there are certain kind of early adopters and very smart people that can be really useful in your design, picking their brains, but they're not the end users as a rule. The end users are regular folks generally. Those folks are not thought leaders, and they will behave differently than your thought leaders. And as a result, yes, take the information of thought leaders, but do not rely on it excessively. Instead, make sure that you're testing out your theories and your designs with real honest goodness, regular people. Okay, so those are the things that tend to cause errors. Now let's talk about the types of errors that are out there. And I've gone back and forth wondering how important it is to really know these different types. Sometimes it's important, and I think it would be useful for you to be aware of them and know how to apply them. But chances are you will not be able to recall them off the top of your head after you've learned them. So keep these notes around. Hopefully they'll serve as useful later on in your career. But don't be surprised if you cannot recall these different things right off the top of your head. Okay, so here's a taxonomy of use errors, a categorization scheme basically for use errors. At the top we have a use error. Imagine that. Those are divided up into two different kinds of use errors. There's use errors where we executed some kind of unintended action. That is, we did something that we did not intend to do. And then on the other side is a situation where we did what we intended to do. It's just that our intention was plain wrong. We were just confused somehow about what it is we were supposed to do in that situation. We executed it perhaps flawlessly, but we executed the wrong darn thing. So let's talk about what those are. This left-hand side, under the situation where it was an unintended action, the first one is called a slip. A slip occurs when you intend to do one thing, but you accidentally do something else. Usually this happens when there's feedback, when this happens, I should say, there's feedback about the result of your actions. You're able to detect the problem and able to fix it. So sometimes when there's not enough feedback, the error might go undetected, and there are a few different types of slips and so forth. So let me see if I can give you, we'll get into details on the types of slips here in a minute. Then I'll be able to give you some examples there. So here's one type, a capture slip. So as I said, this is a use error. We actually did something we didn't intend to do. We executed a slip. This slip is called a capture slip. Here's an example. It's an activity you intended to do, and you accidentally do one that's similar or even shares steps. The accidental activity is more familiar, more common, or more recent than the one you intended to do. And after doing the identical part, you proceed to the more familiar one. Let me give you an example. Every once in a while, on a weekend, I will decide I'm going to go to the grocery store or something. I'll jump in my car, start heading down the street, And instead of going right to the grocery store, I'll go left as if I'm going to the university. Now, eventually I get a little ways down the way and I go, oh my gosh, what am I thinking? It's the weekend. I don't need to go to the university today. Remember, I'm going to the grocery store. And I loop around and go back. That is a capture slip. Here's what happened. Basically, the more frequent and recent activity of going to the university has captured what I intended to do, which is to go to the grocery store. They shared a couple steps. Once I started going down and executing those couple steps, getting in my car, backing up, driving down the road, I went on autopilot basically and did the most frequent route that I usually do, which is to the university when I should have gone to the grocery store. That is a capture slip. You meant to do one thing, but you ended up doing something else that you do more often. That's a capture slip. Now, there's other kinds of slips. There's a description similarity slip. That's when you act on an item that is similar to the target. So, this happened to me. I went in for a blood test, basically at I won't say the hospital, but at a hospital. It wasn't a big deal. It was just regular old blood test. And I'm talking to the technician, and she's making polite conversation and so forth. And I, have my arm out and so forth, my sleeve rolled up. And while she's talking, she wipes down one of the veins with an alcohol swab, just like she's supposed to, and continues talking, and then actually puts the needle in a different vein. Not the one she just wiped down and disinfected with alcohol, but instead another one that never got disinfected with alcohol. That is a description similarity slip. Basically, it was the correct action, right? She took blood. It was just from the wrong vein. It was the wrong target. And you can see where that happens. Two things look kind of similar, and basically you act on the wrong thing. Then there's a mode error slip. Basically, different states of the device have different meanings or modes. So this is common in devices with more possible actions and controls. I'll give you an example. When you are typing and you're sending a text to somebody, and then you look down and you recognize that they're all caps. That is a mode error or a mode error slip. Basically, you had the caps lock on, and when the caps lock on, those same keys act differently than when the cap lock is off. Specifically, they're all caps when the cap lock is on. They're not all caps. They're generally lowercase when the cap lock is off. The same darn controls, those keys, ended up giving you two different results depending on what mode it was in. This kind of stuff happens from time to time. In fact, a very large percentage of errors that occur, and include nasty ones, with pretty negative consequences, tend to be mode error slips. So one example that we talk about in your paper was the Therac 25 radiation therapy machine. That thing has two modes of therapy, the electron beam therapy and the photon therapy. The electron beam, electron beam, provides a constricted low current beam of high energy electrons, whereas the photon therapy delivers X-rays with a beam, unfortunately, that's 100 times higher and over a narrower area than electron beam. The bummer of this was a mode error in which the technician chose the right sequence of actions, but the system was in the wrong mode. The slip delivered a lethal dose of radiation, that is X-rays, and weeks later the patient died from radiation poisoning. That's not an infrequent occurrence. I hate those double negatives. What I mean to say is that this kind of thing happens from time to time. And it's one of the reasons I'm going to encourage you as much as possible to avoid modes. That is, try to make it so that the same controls do not do two different things in two different kinds of situations, like that with the Therac machine or that with the caps lock. It's not always possible, and it gets even tougher and tougher as we miniaturize devices and have fewer buttons on things. But especially in cases where people could be injured, it's really important to avoid that kind of thing. Okay, so those are slips. Now let's talk to you about lapses. Lapses tend to be memory problems. They're breakdowns where the user fails to do what they intended to do. And that can lead to failing to follow steps of a procedure and so forth. The most common one is you're doing something and you get interrupted. And let's imagine you're doing a recipe, you're making something, and somebody comes along and interrupts you, and then you have to go back to making the recipe, and you accidentally skipped some steps because you thought you had done them. That is an example of a lapse. Basically, your memory has lapsed and you ended up missing some steps. And that kind of thing can happen as well. So when that happens, it often has, again, pretty nasty consequences. People can die as a result. We did one project where people reprocess endoscopes. So endoscopes are used for basically doing diagnostic tests in your gastrointestinal system. And as you can imagine, sterilizing those endoscopes afterwards before you use them on somebody else is pretty darn critical because you don't want nasty bacteria getting introduced to somebody else. It turns out doing that required about 202 separate steps, which is just ridiculous. We did a task analysis of it and found that it actually required 202 different steps that had to be done in sequence. Now imagine that the technician doing this reprocessing or doing this sterilization is interrupted, which happens all the time. Now they come back and they can't remember, oh gosh, was I on step 107 or was I on step 112? I think it was 112. And they move on, and in that meantime, they have skipped 5 steps. And those steps could introduce bacteria into the next person who uses the endoscope. That's an example of a lapse. And there's some things you can do via design, and what we ended up doing via design, which is, things like making checklists, making electronic checklists, of course, improving the design of the product itself, which we were not able to do because we were funded by somebody else. But that's an example of a lapse. Basically, you get interrupted, your memory isn't perfect, and you make this mistake. Make this error, I should say. Now let's talk about mistakes. Okay, those first things were things where they were unintended actions. Sometimes we do exactly what we intended to do. It's just that what we intended to do was wrong. That's an example of a mistake. Let's see. There's a couple different kinds, rule-based and knowledge-based. A rule-based mistake is they apply the wrong if-then rule. So I'll give you an example. Imagine that you have a continuous glucose monitor, and you thought that when your glucose is low, you were supposed to administer insulin. Now that's exactly the opposite of what you're supposed to be doing. If your glucose is high, well then maybe you should administer insulin, not the opposite. But imagine you were wrong. You just didn't know very much about diabetes, for example, and you applied the wrong rule. You said, well, when glucose is low, I'm going to take insulin. That would be a really nasty mistake. That would be a rule-based mistake. Sometimes there are knowledge-based mistakes. These are, problem is misdiagnosed because of incomplete knowledge, or the user fails to understand the situation. In this case, because they don't have a lot of information about how something works, they have to try to figure out what to do. And as you know, when we're trying to really figure out what to do and reason through things, we get fatigued, and it's hard cognitive work, and sometimes we ended up doing the wrong thing. That is, choosing the wrong course of action. And that's what happens in a knowledge-based mistake. In all of these things, it's important when there is an error of some kind to do some kind of root cause analysis, which is a fancy way of figuring out what the heck went wrong. So important to doing a root cause analysis is understanding that errors and accidents rarely have just one cause. Often when something bad has happened, several nasty contributors to the error made it possible. So the root cause analysis analyzes those errors until the underlying cause or causes are found. And we get there by continually asking questions until the reason for the failure is revealed. So one of the things we can do to get there is to ask why many times. So sometimes they call them the 5 whys. Sometimes you can get to the answer in 4. Sometimes you don't get to the answer until 10. But they call it the 5 whys. So for example, if an infusion pump was programmed to administer 10 times the dose of a drug, we don't just conclude that the user made an error and call it a day. We want to know why that error was made. Instead, we ask exactly why the user made the error. So perhaps they did something like they pressed a digit twice when they meant to press it only once. Well, why in the world did they do that? Well, we might find out that the keys are too sensitive. And while they pressed the button, they thought it was registering once, it actually double registered. That just tells us that those keys are too sensitive. And now we know what to do to go back and fix it. That would be an example of a root cause analysis. You get to the point where you feel like, now I know what went wrong and what I can do to mitigate that in the future. Related to this is this notion of the Swiss cheese model, which was originally developed by a fellow named James Reason, who's a psychologist out of England. And his argument was sort of errors tend to have multiple contributors, not just one single root cause. And instead, he sort of thinks about it this way. Imagine that you had a whole bunch of fail-safes in place to keep people safe, right? So one might be, instructions, and another might be adhering to conventions, and another one might be, something else. We could have a bunch of them. None of those are perfect. All of those layers of protection have some holes in them that make them not perfect. Now, usually, if one hole is a problem, it's not that big a deal because you get through to the next layer, and that next layer has holes too, but chances are those holes aren't lined up perfectly, and the next layer catches it. So, for example, if somebody doesn't adhere to conventions and they go around that, but they read the instructions, well, then that could keep them from making an error. That is, the second layer of protection ends up helping them. But sometimes the situation is lined up just right. And you can see that with harm number 4 here, where people get through the conventions. They didn't adhere to the conventions, darn it. Oh, they got to the instructions. Oh, they didn't read the instructions, darn it. Now they get to the next thing that was supposed to stop them, and they didn't do that either, darn it. And now we've got ourselves a nasty error. That's the Swiss cheese model. And it turns out that most of these things end up getting through several layers of kind of fail-safes that we might have put in place that we never anticipated they would get through. So there's some things we can do. More layers, for example, will help, or making those holes a little bit smaller so it's less likely people can get through those Swiss cheese pieces. One way to do that is by constraining things in some ways. So we can prevent errors by constraining the types of actions that can be conducted. An example of that, of course, is on the right. If we don't want to plug the wrong thing into the wrong receptacle, well, we can shape code them so that it's impossible for that to happen. And you can see that with all the different kinds of things here. You're not going to plug your DC into the USB type A because that just is silly. Those things look like, they don't go together at all and would probably feel that way too. Another way to do this is undo. And God knows how many times undo and multiple undo has saved me in my work. But to be able to basically undo things that you have done previously gives you an awful lot of ability to discover a system and explore a system without feeling like you're going to do something that kind of ruins all your work. I don't know why this one's in bold, but sensibility checks. Another example to reducing error is to check that the input is sensible. For example, some infusion pumps will not begin infusing a medication volume rate or dosage that's outside normal ranges. So if in that case, if you did accidentally double press something and it ends up being a really high dose, it will ask you, are you sure this is what you meant to do? It sort of provides a confirmation. That's a sensibility check. Okay, well, so that tells you a little bit about use error. And, these use errors, I talk about it a lot, of course, with healthcare. And, in these kind of high consequence kinds of situations like nuclear power, aviation, policing, fire, things like that, they tend to have very high consequences, and those are important. But it's even important just in regular old day-to-day work where you're trying to make somebody more productive, or maybe make somebody enjoy a product for recreation. These kinds of things are still important. You want to reduce the likelihood of people making errors, and once they've made them, you want to figure out how they can go about fixing them without a whole lot of trouble. So thanks for your time. I'll look forward to talking to you next time.